Hi, this is Stuart, and in this video I'll show you how to use the Protosc app to run an analysis. So assuming you've installed Protosc and added it to your path, go to your command window and type Protosc app, such as this. Press enter, and the app GUI will show up. Okay, so let's walk through starting one of these analyses. So I'm going to load images from a single directory. So I'm going to check this box here, and I want two categories of images. So I can leave that as is. Click select, and there will be a pop-up window, and now you can navigate to the location of your images. So I'm going to find the NimStim face set and press open. Okay, so because I'm using images from a single directory, I need to do this step, and that's to add file name requirements to tell Protosc which how the categories are split up by file names. So let's do that. So you get a question in your command window, and it says for category 1, what should be in the file names? So I'll do happy faces as category 1. Now you could also say happy faces and a second term. So sorry, HA is always in the file name for the happy faces. That's why I'm doing it. You could also say I want category 1 to be happy and angry. So then you use multiple terms with an asterisk between them. But I'm actually going to compare happy to angry. So let's just say happy should be included. Now there's no exclusion criteria for me right now, so I can leave this one empty and just press enter. Because I have two categories, the question shows up again. So what should be in category 2? AN for angry. And again, I have no exclusion criteria for the files. Now the images can be loaded. So once they're loaded, you can do all the next steps over and over again on the same images. Okay, so step 4, image preprocessing. What do you want to do with your images? So they're standard loaded as RGB images. So you can choose to convert them to grayscale images, but you could also say, no, I want to convert them to CLab, for example, or you don't want to do anything. I'm going to convert them to gray for now. Because I'm working with faces, there's this extra option that might be interesting, and that's to extract and scale the faces. So this option uses the Viola-Jones algorithm to extract the face area, and Protosc adds a little extra around that area based on a percentage, and then scales all the extracted faces to be the same size. So it's a little better to compare the faces that way, so you don't have to deal with how far the camera was when the picture was taken between people. Of course, that's usually not a big image, but males, females might differ in size, or just individuals might differ in size of their face. And you probably don't want Protosc to pick up on that. So I'm going to scale all the faces. Now this one doesn't do much right now because I'm converting my images to gray, but here you can indicate what channel of the image you want to use. So let's say we are using RGB images, so let's turn gray off for now. But I'm not so much interested in what happens in the green or the blue channel, so then I can just turn them off. And now Protosc will only use the red channel of the images. Now for RGB that might not be most relevant, but for CLab that might be interesting, because we could say, now I only want you to look at the lightness, or I want you to look at A star, which is the contrast between red and green, or for example B star, which is the contrast between blue and yellow. But like I said, for me it doesn't really matter because I want grayscale images right now. The next step, step 5, is to choose how to run your feature analyses. So more specifically, what features do you want to use? So what you like to use for your magnitudes. Now, if you hover over um, each of these boxes, each of these features, we'll get more info on the um, different features. Now, in this case, I would like to do an analysis based on hog features, which are structural components in the face, so it reflects the edges in the face. Finally, choose if you want to link features and if you want to cluster correlated features. So linking features means that it's not so relevant right now because I'm not using color, but for the color settings, it means that all the information from the same color, from the different colors but representing the same thing, is kept together and either selected or unselected as one. The main reason to start doing this was for pixel intensities to deal with color. So let's say you have RGB images, then the actual color of the image is defined, of a pixel is defined by the R, the G, and the B value. So linking those together means that we're using the actual color value for training and for decoding. Clustering means that features that are highly correlated are grouped together and are also selected or unselected during feature selection as one. So right now what we are doing is we loaded up two directories. We gave file name requirements to select images. We already loaded the images. We chose how to deal with the color space, so gray or CLAB or RGB. We said that we wanted to extract and do the analysis only on the face part of the images. This one isn't really relevant right now. So we're saying, well, use all channels, but because we're using gray, it's not doing anything. And I'm saying, well, let's do a hawk-based analysis. So when you're ready, you can press Run Feature Selection, and feature selection starts. Now, I have already ran it, so I'm just going to show you what shows up quite a lot. So here you see what we have in what I did before. So again, I did for category 1, happy, for category 2, AN, for angry. I prepped all the images and read them in, and basically the feature selection starts here. So when you press feature selection, you'll get a lot of output in your command window to show you what Protosc is doing. So it starts with extracting features from class 1, then it gets class 2, then it starts its actual feature selection procedure, and it's standard on standard it uses k-fold cross-validation where k is 10. So it starts with fold 1. It creates univariate ranking. So basically that's the chi-square test to see how different all the features are in a univariate manner. Then it starts correlating the clusters, so it creates those clusters that we saw earlier. It removes features that are that have very low chi-square scores, and then it starts the wrapper, which is one of the 4 approaches of the toolbox. It's the one that takes the longest, so a lot of output refers directly to the wrapper. And basically we get output showing how many features have been selected by the wrapper. It's because the wrapper is the slowest, and I personally like to be updated on what's going on. I never like it when I have to wait for my analysis to be done. After each fold, there's an indication of the performances found in this particular fold. So we see that full model accuracy is 100% correct, and the full model is trying to decode without doing any feature selection. The filter accuracy is already almost 93% correct, even though it's using much less features. Wrapper accuracy is also 100%, and if you take a random selection, you're still about 80% correct. That means that lots of features are probably relevant, because it's very easy to, with a random pick of features from your feature space, you're already doing 80% correct. Pseudo-random tries to make a random selection as well, but it may not take features that have been already selected by the filter or the wrapper, and that does a little worse. This would probably not be significant performance. So this keeps going for all the different, for each fold, and after each fold, you either get this figure, you get it after fold 1, or it's updated. So what can we see here? These are the normalized chi-square scores presented in the reference frame. Now for the hog features, the reference frame is it's the same XY coordinate system as for an image. So you can already see the outline of a face in here, and you can see near the mouth area there's something interesting going on. Those have high chi-square scores. But there's also some stuff around the edges where you would expect that there's no face, and that it shouldn't matter for if someone is displaying a happy or an angry face, but apparently there is some noise there, or at least, well, maybe not noise. There's something going on over there. So what do we see in the next one? This one is the cumulative chi-square. On X it shows the number of features, on Y it shows percentage of the cumulative sum. So why did I build this in? Well, it gives you an idea of how much, how the information is distributed over the different features. So how this curve is created is we take the highest chi-square, that's 0.1. 0.2 is the highest chi-square plus the second highest chi-square. 0.3 is the highest chi-square plus the second highest chi-square plus the third highest chi-square, etc. So if this is a perfect diagonal, all the features have the same chi-square value. And information on what class do the images belong to is all over the place. However, if it's very steep, and based on all the analyses that I've run with this stuff right now, this is relatively steep. If it's on the steep side, you know that there's a few features that hold a lot of information on the class, and lots of features that don't hold any information on the class. So this is just to give you insight in the distribution. Here we see the cross-validation accuracies. The black line is the median chance performance based on a permutation test, so a distribution of permutations basically. The red is the 95 percentile of that distribution, and it's just to indicate how it's going. So we see accuracy percentage, sorry, this should be fraction correct, on Y, and selection method on X. So we have filter, wrapper, random, and pseudo-random here. So we see that the wrapper and the filter do really, really well. We see that random is just above 95 percentile, and pseudo-random is below the 95 percentile. We also have for full, so here no feature selection was applied. And finally, this is the same reference frame as used here, but this indicates the significant features, and their color reflects the associated performance of that feature. So what I found interesting in this particular example is that there are lots of areas which are not in the face, which helped dissociate if, or are relevant for dissociating within this image set, if the images were displaying a happy face or an angry face. Now, and if you look at the images and you go back to them, you can see that there's differences in hair, and people tend to um, rotate their head a little bit, especially when they're angry. They tend to lean a little bit forward. So if I would have done this analysis prior to using these images in an experiment, I would think it's a pretty good idea to present them in an aperture.